All right, let's begin talking about this inference with two proportions. We've just been doing one proportion, but now we're going to do two. So we're mainly concerned about the difference between these two things. So these are actually more common than inferences just about one proportion or about a single percentage. Okay, so this is more common. Think about it. Is the true proportion of patients who experience relief with medicine A significantly greater than the proportion of patients who experience relief with the current medicine on the market, medicine B? Is the true proportion of women who say they frequently experience stress significantly different than the proportion of men who say they frequently experience stress? So, most of our experiments and studies generally revolve around comparing two different values rather than just one to a claim. All right. So we're going to do inference with both intervals and tests, a hypothesis test. And we had started one proportions with an interval, but actually we're going to do this with a test first. We're going to do our phantoms for two proportions before we then do our intervals tomorrow. So here we go. Now, when we do our interval tomorrow, then we could actually estimate the amount, say like the proportion of patients who experience relief medicine A above medicine B. How the higher proportion with what medicine or that kind of thing, and how much more. What proportion of women say they experience stress more frequently than men? So when we estimate an amount, that's what we'll do tomorrow with our two proportion Z intervals. Okay, so here we go. Now, let's take a look at what we have here. We are going to do the two proportion Z tests and intervals, and of course we have to check our conditions. We're going to get real, just like we had previously done that. There's a couple little things different, so I'm going to side by side show you the difference between doing these proportions or doing these conditions and assumptions with just one proportion versus doing them with two proportions. Okay, how do those look different? So, with our one proportion, we stated that amount was stated or randomly assumed to be randomly selected or randomly assigned to the treatment groups. Well, that's the same for two proportions. We just have to say it for both of the samples. Okay, so we have to say both of these samples and we state them specifically. So you'll see in the example how we do that here in a minute. So we do it for both. For independent, we used to just say that the sample size that we have for one group is less than 10% of that population. Well, now we have it for both samples. So we're saying that sample 1 is less than 10% of its population, and sample 2 is less than 10% of its population. Okay? So this, though, is new. So this is the addition that we do, and it is important, and I think you can understand why, that when we have two different samples, we need to confirm and state, and acknowledge. That's kind of what we're doing, acknowledging that these two samples are independent of each other. Because basically, you're then saying, the subjects in this one are also not, they are not counted in what's happening in this other group. Okay, so they're two different sets of subjects. So you're going to verify that they are independent of each other. All right, but now large enough, whereas we used to say, for proportions, at least 10 successes, so N times P. And remember, we want to use true P if we have true P, not the P hat. Okay, is greater than or equal to 10, and then the failures, N times 1 minus P greater than or equal to 10. Well, over here, that is the same, but it is for both of them. So we have to do it for both successes and failures for both sets of samples. Sample 1 and sample 2, at least 10 successes and 10 failures for both populations. Okay, now let's do note one thing, that And I have this written down here below so you can read that. If we frequently, the best it can be is if you use true P. So we would want to do that if we had true P. And with our one proportion tests, we generally have true P. So we use N times that true P. But just FYI, frequently we don't have a true P with two populations or two samples, okay? Because what we are generally doing is we get a sample results from for one proportion and a sample results for the other proportion, the other group, and then we're comparing those two sample results to each other. So a lot of times we don't have the true P. But of course, if you did, then you would use that true P because the true P is the best it can be. All right, well then let's put this into action. Let's see how this looks with an actual problem. So here we go. So we have this example, and this is about smokers. And it's because we are wondering if being part of a support group is going to help people quit smoking. And they are people who are already wearing the nicotine patch. So, a county health department tries an experiment using several hundred volunteers who were planning to use the patch to help them quit smoking. Okay, so they were already motivated to do this, to quit smoking, and they also had already decided that they were going to be using the patch. Okay, so these are the types of people we have. They are volunteers, but we can probably generalize to people like these volunteers who are trying to quit smoking and are choosing to use the patch. Okay. So the subjects were randomly divided into two groups, and people in group one were given the patch and attended a weekly discussion meeting with counselors and others who were trying to quit. But people in group two also used the patch, but they did not participate in the counseling groups. Okay. And so then here are the results. After 6 months, 32% of the 143 smokers in group 1 and 20% of the 151 in group 2 had successfully stopped smoking. Do these results suggest that such a support group could be an effective way to help reduce or help people stop smoking? Okay, so here we go. We're going to go into this and we want to define. So here I have notes. And I have in red kind of written some hints or some help, reminder of what we need to do. And then I have in blue the part that is pertinent to this particular example. So you can kind of see that particular specific example as we go along. So again, I remind you here to define both of the parameters, okay? Use meaningful subscripts, like proportion of women and the proportion of men, that kind of thing. Remember to also use present or future tense, not past tense, okay? Because we don't need to infer about what has happened in the past. That's already happened. So I'm going to choose P with a subscript C to represent the proportion of people who wear a nicotine patch and also attend counseling who successfully quit smoking. So think about this. My denominator is those who smokers who wore a patch and went to counseling, and the numerator is the proportion of those who quit smoking. All right, and then the P with the little p down here, that's the patch only. So that's the proportion of, I guess I should have said who smokers who wear the nicotine patch that successfully quit smoking. Okay, so again, then the difference between those is the counseling or not counseling. So for our hypothesis statements, remember that our null hypothesis is always that those two are equal to each other. Now, you actually have an option of how you can write these hypothesis statements out. One of the ways is the null hypothesis is setting those two particular proportions equal. Okay, but sometimes you may see it as this way. And so you need to be aware of it, but you can choose which one of these you like to use. I personally like to choose this one where I'm setting them equal. But keep in mind, if they are equal, then there is a zero difference between them. So some people will do the define a direction of subtraction and say that's a zero difference. Okay. And then for the HA, the alternative, we're stating what we're wondering about. And we were wondering in this case if the proportion of with the counseling quit smoking at a higher rate. Okay. But here for the alternative, again, you're using the less than, greater than, or not equal to. Okay. Or you can see how I did the P1 is less than, greater than, or not equal to P2. Okay. Or here's the subtraction way. P1 minus P2, and then you have these things less than, greater than, or not equal to 0. Okay, so here's in blue, the context of this problem we're doing. The null hypothesis, I say that they have the same success rate. And then the alternative, I'm wondering if I'm investigating if, so that's why my alternative is this direction, if the proportion who quit smoking using the counseling addition is greater than the proportion of those with patch only. Okay, so here we go. We're going to get real for both of them. So here's my random. So I can say that these 143 volunteers were stated to be, see, they're volunteers, okay, so they are not randomly selected. Okay, but this is an experiment, so they were randomly assigned to one of the two treatment groups. So we had 143 volunteers randomly assigned to the treatment of nicotine patch and counseling, and 151 volunteers were stated to be randomly assigned to the treatment with the nicotine patch only. Independent, that 143 is less than 10% of all smokers on nicotine patch who attend counseling, and 151 is less than 10% of all smokers on nicotine patch only. See how I'm kind of, in a sense, defining those populations as I write this out. Now, here was that special additional thing that is new, saying that these two groups of smokers are independent of each other, because I don't have anybody that I'm counting in this group over here in this group here. They're two separate. Nobody is being double counted in both of those sets. All right. Now here comes our large enough. So notice how the sample proportions was being used because we didn't have a population proportion. So they said 32% of the 143, which is this. And so that's the successes, greater than or equal to 10. And then here's the failures, greater than or equal to 10. Okay, and then for this other group, 151 times that, it said 20% success in that, which was 30.2, greater than or equal to 10, and 151 times 0.80. Okay, so just double checking to make sure that I got that percent correct. Yes, 20% of the 151. Okay, so here we go.